Alright, next, work and electric potential energy. We will look what the relation between work and electric potential energy. Uh, alright, as you recall, the work done by a conservative force on an object only depends on the initial and final position of the object and not on the path taken between those 2 points. That means the potential energy, right? The potential energy function is function exists. Okay, potential energy is a scalar quantity with the change in potential energy equal by the definition to the negative, okay, work done by the conservative force as shown here. Okay. Um, as we know, both the Coulomb force law and the universal law of gravity are proportional to 1 over r squared because they have the same mathematical form, and because the gravity force is conservative, the Coulomb force is also conservative. As with the gravity and electrical potential energy function can be associated with the force. Okay, so to see how it works, okay, imagine a small positive charge placed at point A in a uniform electric field. Okay, this is electric field. Okay, let's assume for now the electric field is constant and that the charge move parallel, move at parallel to the field. Okay, as the charge move from point A to point B under the influence of electric field E, the work done on the charge by the electric field, okay, is equal to the part of the electric force, which is Q times E, this one. Alright, okay. The equation is like here, okay, like here. Okay, we know F, times delta X, so we know F, alright. F here, okay, work done on the charge by electric field is equal to the path of electric force, which Q times E, alright. In the expression Q is the charge, okay, in this expression Q is the charge and EX is the vector component of electric field in X component or X direction, not the magnitude of electric field. So EX can be positive or negative depending on direction of E. Okay, depending of if E. Alright, notice here, in this figure, EX is positive. Okay, so the displacement can also be either positive, okay, can either positive or negative. Okay, this equation below shows the magnitude of the work done by a constant electric field on a charge moving parallel to the field. Okay, this is the big image, right? Okay, we know the charge is moving from high potential energy to low potential energy. What's mean of high potential energy? Okay, the high potential energy is a positive, okay, positive and the low potential energy is negative. Okay, next. Alright, okay, next here we substitute our definition of electric work into work energy theorem. Okay, we substitute to work energy theorem. The electric force is conservative, so the electric work depends only on the endpoint, okay, endpoints of the path A and B, not on the path taken. Okay, that means as the charge accelerates to the right at the figure, the gains kinetic energy and loss an equal amount of potential energy. Okay, means when the electric charge, alright, electric charge from points A to points B, right, this figure, okay, it's gain kinetic energy, um, and but it lost equal amount of potential energy. Okay, all right, as you remember, the work done by a conservative force can be reinterpreted as the negative of the change in potential energy associated with the force. So the change in the electric potential energy of a system consisting of an object of charge q moving through a displacement delta x in a constant electric field, okay, is given by the equation here, where Ex is the x component, okay, Ex is the component x of electric field, and delta x, right, and the delta x is the displacement of the charge along the x-axis. Okay, even though potential energy can be defined for an electric field, this equation is valid only for the case of a uniform, which means constant electric field for a particle that undergoes a displacement along a given axis. Okay, here we call is x-axis. Okay. All right. Okay, this another example. Okay, this the another example or another figure. Okay, when a positive test charge move from A to B, the electric potential energy decrease. Okay, because it's from the because it's gain kinetic energy but lose uh, of potential energy. Okay, same with the energy of the object. Okay, okay, we can see the object. Okay, the object with a mass move from A to B. Okay, the gravitational potential energy will decrease, but the object is gain the kinetic energy. Okay, this figure is show you about a comparison of electric and gravitational field. Okay, but the kinetic energy is increased. Okay, one major difference between electric and gravitational potential is there are two kinds of electric charge. Okay, which is positive or negative charge, but gravity has only positive gravitational charge of or mass. Okay, negative charge particle at rest at point A in the figure would have to be pushed down to point B. To see why, let's apply the work energy theorem. Okay, energy theorem here. Okay. Okay, to a negative charge, to a negative charge at rest at point A and assume to have some speed v. Okay, assume speed v on arriving at point B. Okay, notice that the negative charge had a positive charge in electric potential in moving from A to B. If the negative charge has any speed at point B, the kinetic energy corresponding to the speed it is also positive. Because both terms on the right hand side of the work energy equation are positive, there is no way of getting negative charge from point A to point B without doing positive work on it. In fact, if the negative charge is simply released at point A, it will fall uh, upwards again the direction on the field. Okay, is the equation. Okay. Okay, electric potential. Okay, let's define an electric potential difference. Okay, we will define the electric potential difference or delta V between point A and points B as the change in electric potential energy as a charge Q move from A to be divided by the charge Q related to potential energy. Okay, the SI unit for electric for potential difference is joule per coulomb or V. Okay, all right. Because the electric potential energy is a scalar quantity, so electric potential is also a scalar quantity. From this equation, okay, you can see the electric potential difference is measure of the change in electric potential per unit charge. Okay, you can also think of the electric potential difference as the work per unit charge that will have to be done by some force to move a charge from point A to point B. Okay, in electric field. Okay, take a look at the unit. For special case of a uniform electric field like the field between charged parallel plate, we can divide our potential energy by Q to get the equations shown here. Okay, the result show the potential difference also has unit of electric field time distance. It show here. Okay, so that means the SI unit of the electric field is the field. That means the SI unit of the electric field is the Newton per coulomb, can also be expressed as volt per meter. Okay. All right. Remember the equation of delta Vx is valid only for the system consisting on a uniform electric field on a charge moving in one dimension only. Okay. Okay, it means the release from rest, positive charge accelerates spontaneously from regions of high potential. Okay, remember the figure. Okay, this figure. Okay, uh, the initial velocity in the direction of high potential to the low potential energy. Okay.